Okay, good afternoon. Today we're gonna wrap up Zener diodes, voltage regulators, and hopefully finish up clippers and clampers. My target was to finish up the diode chapter, but well, let's see how much we can cover. So, where is all right? Okay, so quick and brief recap. All right, so we introduced Zener diodes. Zener diodes have the property of being operated in the reverse bias. They hold the voltage across their terminals constant. This property allows us to use it as a voltage regulator. Regulation or voltage regulation means changes in supply voltages or changes in other parts of the circuit. And regulation means keeping the output voltage constant regardless of what changes in the circuit. Okay, those changes could be series resistances, load resistances, and also supply voltages. All right, so we started discussion with an idealized version, meaning we just had a simple Zener diode. We are applying V in on the left and obtaining V out on the right. Obviously, this is not possible in real life because if you apply a voltage source to a Zener diode, voltage source have the property of keeping the voltage across their terminals constant. So we cannot have V in the same and VZ the same at the same time, right? So we introduced a series resistor RS between the supply voltage and the Zener diode. The series resistor RS allows us to control the total supply current that's coming from our voltage source. Now, based on this configuration, we can look at a few rules, few assumptions, and few quantities. Oh. All right. The first one is that the total supply current coming from the left, let me mark it here. This is where the total supply current is coming from, IS, right? IS goes to the series resistor RS, and it splits into two, IZ and I. Now our book uses R and I for load. I don't like that. Typically, I like subscript notations for everything. So in class, I will use RL and IL for load resistor and load current. Again, you're an engineer, so you, over the course of your career for the next few decades, you'll encounter many different subscripts, many different notations. So it'd be up to you to recognize, what is being talked about. So this would be I or IL. Just letting you know that in the book, just references without any subscript notation. All right. So load current, load resistor. So we can see total supply current coming from VS is split in two. So that's the first thing. IS is equal to IZ plus IL. KCL at the top, right? Simple branches. There's nowhere else for the current to go through except those two parallel branches. Secondly, the load is connected in parallel to the Zener diode, which seems kind of obvious because we want the voltage to be constant at the output load. And so VL, the load voltage, would always be equal to VZ, the Zener voltage. Right? If there are any changes, then it's not regulating. If it's a properly designed regulator and the circuit is functioning as intended, then VL will always be equal to VZ. So in most books, most classes, most authors will simply use VZ for the output voltage. Okay, they would not use VL. They would simply state VZ. That's it. Because VZ is the one that's being collected at the output. So that's the second point to keep in mind. Third is the load current IL. And that would simply be given by VZ or RL. Well, technically, we are applying Ohm's law to the load resistor. So V equals IR. VL is equal to IL times RL. But VL is the same as VZ. So load current IL is VZ over RL. And then finally, the fourth point is that this total supply current IS can be determined by applying Ohm's law to RS. RS has two voltages on either side. On the left side, it has the supply voltage VS. On the right side, it has the Zener voltage VZ, right? Common terminals. Common terminals for VS and VZ. VS on this side, VZ on this side. So the difference between the two ends of the resistor is VS minus VZ. Node voltage analysis. Did you all do node voltage analysis 115? Yeah. And so IS can be determined as VS minus VZ for RS. Do you all remember node voltage analysis? Mesh current analysis? Can you apply those techniques? Some nods, that's good. Some nods and some shakes. All right. So based on these, based on well, the observations and the rules that we just saw, we can say there are three things or three quantities that can change the circuit. First one is obvious, that's the supply voltage, right? Supply voltage can change, and that is all, of course, also the most common. Second is the load resistor RL can change, right? You could take the same power supply or same regulator and you could connect it to different loads. So the load resistor RL is changing. No matter what is changing in the circuit, the job of the Zener diode is to keep the output voltage constant. In a theoretical circuit, Zener diode would function without any limit. But in a practical circuit, all of these variations, all of these changes require some constraints on the design or impose some constraints on the design. All right, so I'm going to go up here. I'm going to use this use net space. So if there are changes in RL, and Zener diode regulates the output voltage to be constant, then that process is known as load regulation. If there are changes in the supply voltage Vs, meaning the power line that's coming from the input, then the regulation is known as line regulation. Okay, load regulation and line regulation. So based on these variations, there is a maximum and a minimum value for both RL and Vs. Okay, there's a maximum and minimum limit to both RL and Vs. So far, so good. Okay, so what happens if Vs increases? What's the first thing that comes to mind if voltage supply increases? Actually, I should have started it down here. Supply current IS increases, assuming all other things are constant, right? Zener diode rating is not going to change. That's going to remain constant. RS, once we choose it, once we design it, it's going to remain the same. But now if the supply voltage changes, then IS increases. If IS increases, let's observe from this first equation. So Vs increases, therefore Is increases. If Is increases, then Iz and IL both should increase. But the purpose of the circuit is that voltage at the output remain constant, meaning the load voltage VL must remain constant. If load VL is constant, RL is constant, then IL is also constant. So what happens to IZ? So correspondingly, IZ also increases. So if VS increases, IZ increases. Remember last class I stated the Zener diode will absorb more current coming from the supply to keep the output current constant. That's what that point is. Did that make sense? Let's take a pause and let me know if you have any questions. Any questions? If IZ increases, what happens to the Zener diode? It's receiving more power, it's receiving more energy. So the power dissipation increases. Electronic devices, most of the power dissipation is released as heat. Devices get hot. Hence, there is a maximum power rating on these devices. So IZ value is constrained by PZ max. Hence, remember the important two important parameters in the spec sheet: VZ, the Zener voltage, and PZ, the power rating. So Vs is constrained by PZ max. Okay. Vs has a maximum limit. And minimum limit is obvious. If it falls below a certain level, the diode's not going to turn on. So now, if RL changes, decreases or increases, we'll look at both cases. If RL increases first, what happens to IL? Ohm's law, resistance increases, so IL increases. IL decreases. If IL decreases, then where is the extra current going? To the Zener diode. The Zener diode must absorb the extra current, so IZ increases. Again, remember, IS is going to remain constant, right? Because RS is constant, VZ is constant, VS is constant. Now, RL is changing on the far right. RL changes, that changes IL. Okay? Any changes in IL would affect the Zener current IZ, both in the upwards and the downward direction. Okay. So if RL increases, IL decreases. If IL decreases, then IZ must correspondingly increase. If IZ increases, again, you're constrained by PZ max. Therefore, RL max is constrained by PZ max. Okay. RL max is constrained by PZ max. And on the flip side, if RL decreases, then IL increases. If IL increases, then it's going to require more current from the power supply. So IS increases. But if RL decreases, you apply Ohm's law to the output, then the voltage across that load resistor is going to decrease. So VL decreases. And the VL is less than VZ, the diode's not going to turn on. There's no circuit regulation. Therefore, there is a minimum value of RL. And we'll see that in the next two design problems. Okay. Okay. Design. All right. So we have a standard circuit, Zener diode, series resistor, load resistor R. We are given a supply voltage of 24 volts. So on the left, we have 24 volts. VZ is given to us as 12 volts. So on the right, we have 12 volts. We have IS coming from the supply. So IS, IZ is going down the Zener diode. This I'm going to call IL. And this is going to be RL. In this particular instance, RL is given to us as 250 ohms. RS is already given to us as 50 ohms. All other quantities remain constant. Okay. The question being asked is, what is the maximum power dissipation of the Zener diode under these circuit parameters and under worst case conditions? Okay, worst case conditions. So worst case conditions depends on the quantity we need to find. Okay, from the previous slide, we saw that there's a minimum and maximum value for V in, I mean, the supply voltage. There's also minimum and maximum values for the load resistor RL. There's also minimum and maximum values for for the series resistor RS. All of those are part of the circuit, right? So variation or change in any one of those quantities is going to affect the entire circuit, and load regulation may not occur. So any one of these quantities goes out of bounds, that's like a worst case scenario. Okay. In this case, we are referring to maximum power dissipation. Okay. Maximum power dissipation. The key word is power. Power for the Zener diode is the product of the Zener voltage and the Zener current. VZ is going to remain constant. So worst case scenario is fluctuations in IZ. So that's the approach we need to take with this design problem. Okay. So we need to find PZ max, maximum power dissipation in the Zener diode. That requires us to find IZ max, right? And IZ max will occur when IL is what? IL is at? What happens to IL if Zener diode is maximum? It goes to minimum. IL goes to minimum. Load current goes to minimum value. What is the lowest value possible for IL? KCL, right? IS is IZ plus IL. If IS is maximum, IZ is maximum, and IL is at its minimum value, what is the lowest value IL can take? 0. Load current is 0. If load current is 0, what is the value for RL, load resistance? There's only one possible value for 0 current. Lazy 8. Infinity. RL has to be infinity, which means worst case condition would be no load is connected at the output. If there is no load connected and you have a supply turned on, everything's going to the Zener diode. All right, let's find IS first, because IS requires VS, VZ, and RS. We have all three. So VS minus VZ RS is 24 minus 12 divided by 50, which is 0.24 amps. And we can find IL for these conditions, standard conditions. We are not looking at worst case just yet. It would be VZ or RL. VZ or RL is 12 over 250, which is 0.048 amps. And from here, we can calculate IZ. IZ would be equal to IS minus IL. And that turns out to be 0.192 amps. So for the circuit parameters given as is right here, maximum IZ value would be 0.192. And therefore, the power dissipation in the Zener diode as given, VZ times IZ. 0.192. And that is 2.304 watts. Okay, 2.304 watts. This is not yet worst conditions, right? This is with the load. Load is 250 ohms. Worst case is just coming up next. We'll just take load equals infinity, meaning IL is 0, and then IZ is equal to IS. Knees are getting tired. Old age. Okay, worst case conditions. Worst case conditions in this case is if IZ goes max, which is when IZ would equal IS, and that would be 0.24 amps. And therefore PZ max would be equal to 0.24 times 12, 2.88 watts. Okay, 2.88 watts. So if you're using the circuit as is with no changes in RL, you could have a 2.3 watt Zener diode. That would be pushing the limit. But if there was no load connected, then you would require Zener diode to be at least 2.9 watts. Probably 3 or 3.5 watts, just to be safe. All right, let's take a pause. Think over that. Let me know if you have any questions.